Test, test. All right, here we go. Let's see, so I've got a spring, and it is attached to the roof. And it's sitting there, and I attach a mass to it, and we let it get down to its equilibrium position where the forces are equal, and then we pull it down 0.2 meters, and we let it go. What's the amplitude of motion? Well, then the amplitude of motion is going to be 0.2 meters. Not much there to mess with. How much time until it returns to the starting position? Well, that's a period question. Period is equal to 2 pi square root of m over k. So 1 divided by 9.87 square root gives me times 2 times pi, and I get 2 seconds. 2 seconds. And so I want to return to the starting position is 2.0 seconds. Time is released. How much time until it reaches? First time it reaches the, it should be equilibrium position. Equilibrium position. Okay, so how much time until it reaches the equilibrium position? Well, okay, that would be when it gets, when I pulled it down 0.2, it's when it gets back to this middle position, right? So that would be 1/4 of the whole trip. And so 1/4 of 2 is 0.500 seconds. What time would it reach the highest position? Well, once it gets, that would be all the way up here, right? That'd be halfway through its trip. Half of 2 is 1 second. How fast is it going past the equilibrium position? Well, when it goes back to the equilibrium position, the spring is no longer applying a force on it, correct? The spring is not stretched at all. The spring distance is x is equal to 0. So energy before equals energy after. Energy before is going to be equal to 1/2 kx squared. Energy after is going to be equal to 1/2 mv squared. There's going to be no spring energy at that point. Why did I pick spring energy? Because I know when I pull it down 0.2 meters, I know where it is, right? I know that's, there's no additional energy. I'm letting go of it, so there's no kinetic energy at that point, right? So 1/2. K is 9.87. X is 0.2 squared equals 1/2. M is 1. V squared, right? So the halves cancel out. And I get 9.87 times 0.2 squared. And I'm going to take the square root of that, and I get 0.628 meters per second. So my velocity is 0.628 meters per second in the middle. 0.628 meters per second in the middle. Okay, how fast is it going at the highest point? Well, once it gets to the highest point, it's stopped, right, before it turns around and goes back the other way. So therefore, how fast is it going at the highest point is 0 meters per second. How fast is it going at the very bottom spot? Well, the very bottom spot's where we let go of it, and once it gets back there, it has no more energy except for that which is stored in the spring. So therefore, it'll be 0 meters per second. In other words, it's also going to turn around that point, so that's to be going 0. Sketch the amplitude versus time for the first 8 seconds. So if I do amplitude versus time, I would start in negative land, right? I'm starting at the bottom. This is 0.2. This is 2. I'm going to go 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds, 8 seconds. Isn't this fun? Okay. It's starting at -2. At 1 second, it's at 2. Halfway, it's at 0. Then back down to 0 and back to the beginning, right? And then it's going to rinse and repeat. Every 2 seconds, it is back where it started. Every 1 second, or every second in between, it's going to actually be the topmost spot. So it's going to be look like this. And indeed, you learned in trig how to turn this into an equation, if you absolutely needed to. Unlikely to need to. What's the potential energy? Well, the potential energy is the energy stored in the spring, in this case, is what they're talking about. And that can't be negative, although they almost always give you a negative field to play with. So at the very beginning, so if we go 1, this is 2, 4, 6, 8. When it's at the very bottom, it has maximum potential energy. When it's at the very top, it has maximum potential energy. So it also has it at 1. It also has it at 2. It also has it at 3. It also has it at 4. It also has it at 5. It also has 6, 7, and 8. And so what's going to happen here is it's going to go, woo. Whoops, I screwed that up. All right, go down, back up at 1, at 2, at 3, because what's at equilibrium has no potential energy, right? What? Oh, no. Okay, so that would be its energy. Okay, so that's potential energy versus time for the first 8 seconds. Now, for those of you, as you're starting to think about the next problem, what's different about when something's going back and forth? Well, what is different about something when it's going in a pendulum motion? The only thing that's really different, everything else is going to work out almost exactly the same. We're talking about displacement, we're talking about how far in the x direction. We're not talking at all about the y direction, except for in this thing. What energy is driving a pendulum? It's potential energy, right? And so you're going to have to figure out mgh, right? When you do energy before x, energy after, it's going to be mgh is equal to kinetic energy at the bottom. Okay? We've already done problems like that, so that shouldn't be too shocking. Might require a little work to figure out that math, and hopefully you guys will do well on it. All right, so this is the how to do problems on assignment 10-2 for you guys.